welcome to lesson 28 for Math 135, Missouri State University. We're going to make a little bit of a shift here today, and we're going to talk about sequences and series. And we're going to have several lessons here in a row, starting out with some basics, then we'll look at some specific types of sequences and series. Okay, so let's get started. Lots of times we like to kind of play this game, what's the next term? Of course, I should say, what is a reasonable next term for that? And if you'd like to take a few minutes and play with this, you might want to put me on pause and play with these sequences and see if you can list the next three. Because I'll come back in just a second and we'll run them through. Well, if you've played with it, you might realize that the next number should be 25, and then 36, and then 49. Do you know what the pattern was going on here? These are all perfect squares. 1 squared, 2 squared, 3 squared, and so on. Okay. For this next guy, I would put 16, then 19, then 22. The pattern I'm seeing is I add 3, I add 3, I add 3, so I just kept that particular pattern going on. Oh, by the way, I saw this as a pattern of squares, and that's what I mentioned. I have had some students say, oh, I added 3, and then I added 5. And then I added 7, and then I add 9. That pattern works well as well on that one. This guy, you can kind of see we're counting backwards by 5s. So I see this as 55, 50, 45. Okay. And then number 4 is kind of interesting here. Your first thought is there is nothing going on here. But the 5/12 and then 2 terms later having 7/12 to me kind of is the biggest hint, because I could write 1/2 as 6/12. So believe it or not, I am simply adding 1/12 each time. So the next guy would be what, 8/12, 2/3. Well, that doesn't look good. And then 9/12, which would be 3/4, and then 10/12, that would be 5/6. I thought that was kind of a nifty deal that the 12ths kept reducing. So it was a little hard to see that particular pattern. All right. Well, then we have to talk about some of the basic ideas and some of the notation that goes along with this concept. A sequence is actually a function, and we have studied functions. You know that functions have a domain and a range. And the domain for a sequence is actually the set of positive integers, so we're talking about 1, 2, 3, 4, and so on. And the range, or the output of that function, is going to be this list of numbers along the way. And I'll try to help you see that as we go through some of these. Well, then the question is, what does this notation mean? A with a subscript of n. Well, that is called the nth term. So for example, in a sequence, the way it works out is we call the first term a sub 1, the second term is a sub 2, the third term is a sub 3. So if just out of nowhere you see this notation, a with a subscript of 53, and you say, well, what would that be? It would be the 53rd term in this list. And do you see that the idea here is my domain? What I put in is this subscript. And then what would come out of the function is whatever that number happens to be. Remember, we just had some lists. So in fact, if I go back to that for just a second, this is a sub 1, a sub 2, a sub 3, a sub 4, and so on. So I could say that if I'm looking at this particular sequence in number 2, a sub 1 equals 4, 1 is the input, 4 is the output. And that's what I meant when I said that the range is essentially this list of numbers. Okay. Well, one of the first things we want to look at is that there's two main types of ways that we can define sequences. One is called a recursive definition, and in the case of the recursive definition, and we'll do some practicing with this, but recursive means that you have to find these terms in order. You have to find the first, and then the second, and then the third. You have to walk this sequence out one step at a time. Now, an explicit definition allows you to find any term you like independent of any other term. Meaning that if I suddenly want to know what the 15th term is, I don't have to know the first 14. I just go straight to the 15th term. Now we're going to do some practicing with these ideas, okay? So I said let's determine if this definition is defined explicitly or recursively, and we want to write out the first 4 terms. And in fact, I suggest that you get in the habit of trying to write out terms because it often helps us then try to analyze if there is a pattern going on there, if it's one of our special sequences. Now, remember, this is a function, and that subscript is my input. So if I'm looking for a sub 1, it means temporarily n is 1. N equals 1. So I simply put in a 1 in this place, and I end up with 2 minus 1, I get 1. On this second guy, for a sub 2, n will be 2. So temporarily, for this particular term, n has to be replaced by the number 2, and we get 2 times 2, we get 4 minus 1 is 3. Okay? For a sub 3, n is 3. Now, again, I know the notation might be totally new to you. Don't get too fretted about it right now. Take time. And pay attention to the idea that that subscript tells you which term you are looking for. And this rule for the function generally tells you what to do to get that term. Okay? Well, if n is 3, I get 6 minus 1 is 5. And if n is 4, I get 8 minus 1, I get 7. So my first 4 terms, which I could write as a sequential list, hence call it a sequence. 1, 3, 5, 7. And a lot of times we just write it in that way with commas, and I could put the extra dots telling you that this sequence can continue on. I'm just giving you the first 4. And then you know if you come upon this notation, here's my first term, my second term, my third term. This guy is a sub 4. That's the notation. Okay. I have seen a few authors that didn't use the letter A, but most authors will use the letter A with a subscript to name the terms. Now, the question is, before we leave this guy, is this defined explicitly or is this defined recursively? Well, look at the definition, the rule for my function. Can I just immediately hop out to the 20th term if I wish? Like, could I just find a sub 20? Well, that would be 2 times 20. Minus 1, that'd be 39. Yeah, I can do that, which means that this is an explicit definition. Okay? Well, we're not done. We'll practice a little bit more here and help you get more comfortable with it. Second sequence, I tell you a sub 1 is negative 10. Well, that's nice. That's telling you the first term. All right, my first term is negative 10. And then it says a sub n is equal to a sub n. What? Okay. Well, since I already knew what a sub 1 was, I can go ahead and write that in. Now, to get a sub 2, here's what I need to think. Let's come over to the board for a second. If I'm looking for a sub 2, do you realize that subscript tells me n equals 2? Now that means that for the time being, n has to be 2. So my rule there says that I'm supposed to then use a sub 2 minus 1 plus 5. Because n is 2, so it replaced this n also with a 2. Well, if I rewrite that, I simply get a sub 2 is a sub 1 plus 5. And then you might say, oh, wait a minute. I know what a sub 1 is. A sub 1 is negative 10. So what we did here is we replaced this with what we know it's equal to using substitution principle. And then I end up with a sub 2 is negative 5 when I combine those. So a sub 2 is negative 5. Well, now I need to find a sub 3. And so I say, all right, well, if I need a sub 3, what does that mean n has to be? Means right now n must be 3 for the time being. So then I go to the right side of my rule and it's 3 minus 1. Well, of course, that means that a sub 3 is equal to a sub 2 plus 5. And you say, well, what's a sub 2? Well, I just figured out that a sub 2 is equal to negative 5. So we can substitute that in. My a sub 3 is going to be a sub 2 plus 5, and so then I replace that guy, and my a sub 3 will equal negative 5 plus 5. He'll be equal to 0. Hey, you might start to see a pattern, and you might decide you can move a little bit quicker, but then again, you might also decide, well, I'm not ready yet. I'll go ahead and write it up here. For a sub 4, that means that n is 4, so I will have a sub 3 plus 5. Notice this guy needs to lag 1 behind. And I know a sub 3 is 0, so a sub 4 is 0 plus 5. He is 5. And so then my list is negative 10, negative 5, 0, and 5. Now, by the way, let's kind of take a look at what we really have here and see if we can kind of see a bigger picture of it. Do you realize that essentially what we're doing each time is taking the term before and adding 5? So we have negative 10 plus 5, negative 5 plus 5, 0 plus 5. Okay, so we do see that pattern, all right? Now, is he explicitly defined or is he recursively defined? So the question is, with this given information right here, and you know we were given both of those pieces of information about our sequence, can I immediately hop out and find the 20th term? Well, to get the 20th term, I need to know, I need to know the 19th. But to know the 19th, I'd have to know the 18th. This is a recursive definition. it is recursive because in order to get the sequence listed out here, I have to find the first and then the second and use that to find the third and use that to find the fourth. Now, by the way, this is a special sequence, and I know some of you might say, oh, I can tell you what the 20th is. Well, that's great. But as far as the definition is concerned, the definition is recursive because if I'm going to simply follow this definition, I must walk it out one step at a time. Okay? Well, now in this particular case, we're told that a sub n is going to be 2/3 raised to the power of n minus 1. So, if I'm looking for the first term, remember that means that temporarily n is 1. So I have 2/3 to the 0, which would be 1. If n is 2, to find the second term, I would have 2 minus 1. So I would have 2/3 to the first power, which will end up being just 2/3. I guess I could have written this on the first guy. That's 2/3 to the 0. Now to get my third term, n is 3, 3 minus 1. That'll be 2/3 squared. That will be 4/9. And for the last guy, if I'm looking for the fourth term, remember, this is called the nth term. To get the fourth term, I would have 2/3 raised to the third power. It'd be 8/27. And I can make a nice sequential list if you'd like. Okay. And is it explicitly defined or is it recursively defined? Well, if you think about it, can I go immediately to the 20th term? Immediate's a relative term here. A sub 20 would be 2/3 to the 19th. And yeah, I can't tell you what 2/3 to the 19th is off the top of my head. However, I can't immediately get to that 20th term. So this is an explicit definition. Okay? Meaning, in order to get the 20th term, I did not have to know the 19th term. Okay? Are you kind of getting the gist of how these work? Well, I think this is our last guy to play with. And look at how nice this is. I'm asking you to list 4 terms, and I give you a sub 1 is 1. I give you a sub 2 is 1. Well, we're halfway done. Now, to get a sub 3, since it's not given to you, I've got to use this rule for the function. And so that would be a sub 3. Notice I'm looking for a sub 3, so n is 3, is going to equal a sub 3 minus 1 plus a sub 3 minus 2. And then you go and you look to see if you've got those values. Well, a sub 2 is 1 and a sub 1 is 1. So this ends up being 1 plus 1. Not too tough of arithmetic. We get a 2. Yeah? Well, then to get a sub 4, okay, I'll just start that over. Thought I could just erase the subscripts, but it's not going to be that friendly to me. To get a sub 4, we would do a sub 3, right, because 4 minus 1, plus a sub 2. And so we're adding 2 plus 1. We get a 3 out of this. Yeah? So written as a sequential list, I get 1, 1, 2, 3. And I think I hear some of you saying the next few terms. I hear you saying 5, 8, 13, 21, 34, 55. What is this called? This is a famous guy. He actually has a name. He's called the Fibonacci sequence. If you like, you could do some research on that Fibonacci sequence. Some think that he has connections to nature and so forth, but he certainly is an interesting and kind of fun little sequence to play with. Now the question is, was he defined explicitly or recursively? Well, did you need a previous term in order to get the answer, or could you just immediately hop out? If I want, for example, if I want a sub 20, in this case, what do I have to know? Well, interestingly, in this guy, I have to know the previous two. I would need a sub 19 and I would need a sub 18. So this guy is definitely recursive. And again, if you're going to go off and do some research on him, there is an explicit formula for the Fibonacci sequence, but he's not so pretty and easy as add the previous two. But you can check that out. Well, we're going to make a little bit of a switch here because of some of the notation we have to deal with, and it's find 5 exclamation. It is amazing how much we use punctuation in math. What does this mean? Okay? Well, here's essentially what it means. That is called a factorial. And this would be read as 5 factorial. And what we mean anytime you have a factorial is that you will start with that number and then you will multiply times each positive integer less than that number. So it's 5, 4, 3, 2, 1. Now I know I do not have to put that 1 because it has no impact on changing the answer. It's just habit. So that's 5 factorial, which I believe if you multiply that all together, you get 120. If I had 7 factorial, that would be 7 times 6 times 5 times 4 times 3 times 2 times 1, and I believe that's 5,040. Kind of interesting with these factorial guys. You might play with your calculator and see what the biggest factorial is that your calculator will give you, assuming you don't have a really high-level fancy calculator, and you might be surprised at how low that number is. Because you know, there we are at 7 factorial, already equaling over 5,000. Okay. Well, so what in the world will 8 factorial divided by? If you have done some probability in the past, you might recognize that particular arrangement of numbers. We have to do this when we're working with combinations. Now, in order to do this arithmetic, that would be 8 times 7, 6, 5, 4, 3, 2, 1. That's a whole lot of numbers. And of course, the numerator is like 40,320 or something, and the denominator is 120. That's not the route you want to go, all right? What you want to do is you want to cancel. So for example, I see this nice long string of 5 times 4 times 3 times 2 times 1. They're all common factors. And then I see 3 times 2 here, which will cancel with a 6, and just like that, that big old ugly number ends up becoming 56. Okay. And because I told you that these numbers will get huge on your calculator, it does really help if you can write those down and do some canceling sometimes. Especially with something like this. Because if you took my advice, you found your calculator will not tell you what 100 factorial is. Hey, you know what's interesting? I'm talking about your scientific level calculators. Your scientific calculators will give you 9 times 99999 times 10 to the 99th, because it'll go into scientific notation. So do you notice what's just a teensy bit bigger than that? Essentially, it'd be 1 times 10 to the 100th. You might know that guy is the Google, because this guy overloads your calculator. He is bigger than a Google. That's pretty impressive. Okay, so how am I going to do that? Well, now don't worry too much. I'm not going to write these all out. Okay, now here's what I did. I started writing out the 100 times 99, 98. Oh, good night, I'm not going to write all of those. But we know it's going to end times 3, times 2, times 1. Now, 3 factorial is simply 3 times 2 times 1. And then this 97 factorial is going to be 97, 96, 95, all the way down to 1. For quick arithmetic, what can we do? Well, I would certainly cancel that string out. Take the longest string that you can. Now, as it turns out, you can also cancel some here and help out the arithmetic, but I decided I didn't want to stand here and do that arithmetic, and so, hopefully, we see that the answer is 161,700. I'll just go ahead and erase these guys since they all canceled out, so you can see that answer better. Okay, and we have just one more of these factorials to play with. The reason we're playing with them is that as you're working with some of these sequences, these factorials will come up. They just kind of naturally arise with some of our sequence work, and your author sometimes throws some of these problems at you. So I want you to have some idea of how to deal with them. Now this last one is going to be a little bit scary, because it's all n's. Well, we know what we're going to start this guy with. We're going to start here with n plus 2, right? Just like we started 100 factorial with 100. Well, what number is 1 less than n plus 2? That would be n plus 1. And what number is 1 less than n plus 1? We'll take away the 1, that'd be n. And what's 1 less than n? N minus 1. And you know, even if I was inclined to, I can't write them all out because I don't know what they all are. But I know that they're going to continue down and end with times 3, times 2, times 1. Hey, do you remember what these guys are called with the exclamation? Factorials, right? Factorials. Then n factorial would be, I'm starting it at n. What's 1 less than n? N minus 1, and then n minus 2, and so on all the way down, times 3, times 2, times 1. And then if you look really carefully, you'll realize that in both cases I go from n all the way down, and so I can cancel all of that, and I am simply left with those two. Now, can you multiply those guys together? Hopefully, we get n squared plus 3n plus 2. Now, if you didn't get that 3n, you might want to go back and refresh your memory on FOIL multiplication, okay? Well, now that we've got a little bit of experience with factorials, that's a good thing. Then we get another kind of new symbol popping up at us when we're working with sequences, and then we start adding them up, calling them series, and that is the great big sigma. And we use the great big sigma in mathematics to mean sum. Add it up. For example, the first sum I'd like to do is this monstrosity. And you look at that and it just looks scary. What in the world does that mean? All we need to do is take a little bit of time and get comfortable with the notation, and you'll see it's not a bad thing at all. Now here's the way you read this guy. You say the summation. That means sum up stuff. The summation as k goes from 1 up to 5 of 3k. Okay, that's how you say it. What? Here's what it means. You first let k be 1. And this is just like we were working with the n before. This is a temporary thing. If k is 1, we get a 3 out of this. Then we add. What do we get when k is 2? Because we start with k being 1, and we increase it by 1 each time until we get up to k being 5. That's where we stop. Well, if k is 2, we get 6. And if k is 3, we get 9. If k is 4, we get 12. And if k is 5, we get 15. So here's exactly what this guy means. And I wrote these underneath so that you could kind of see where this was coming from. But if I leave those off, this sum would look like 3 plus 6 plus 9 plus 12 plus 15. Do you see that I have a sequence of numbers going on there if you ignore the plus signs? If I simply wrote 3, 6, 9, 12, 15, that would be a sequence, a listing of numbers. If I put the plus signs in there and I start adding up these terms, it becomes a series. This is going to be a series. This is a sequence. Okay? And then what we can do is what's called a partial sum. This sequence, you can see, he's just multiples of 3, and I could just keep writing him for the rest of my life. Well, then I don't necessarily want to add them all up. I want to add up a partial list, and that's called a partial sum. So then you simply add, we get what? 9 and 9, 18, 30, 45. So this sum equals 45. And by the way, since I'm adding up 5, this is the 5th partial sum of that particular sequence. Okay? Well, going on. I give you a different summation to look at here. The sum as k goes from 1 to 3 of 1/2 raised to the k. Well, how am I going to find that? I start with k being 1, so I have 1/2 to the first. Then I let k be 2, so I have 1/2 squared. Are you okay with that being 1/4? 1/2 squared? Then I let k be 3, and I get 1/2 to the third, which is a 1/8. I only have 3 terms, so it's no problem for me, I can just add those up. It's what, 4/8 plus 2/8 plus an 1/8. I think we get a 7/8 on that guy. So that would be a partial sum. Now, by the way, if I'm looking for the sum as k goes from 1 to 5,000, I don't want to write them all down and add them all up individually. And so as we go on through our study with sequences and series, we will find some ways to try to help us with those big jobs. Here's one that'll be a little bit of a big job. I want the sum as k goes from 1 up to 50 of 8. And you say, what? Okay. My sigmas aren't so good, so I'll save one. Okay, here's what we've got. The sum as k goes from 1 to 50 of 8. Well, let's see here. If k is 1, temporarily k is 1, and I put a 1 in for k, but I don't have a k. Well, then I guess the answer is 8. Then I put in a 2 for k. Well, there's nowhere to put it. The answer is just 8. And then I put in a 3, and by now I'm starting to get the gist of this guy, and I put in a 4. So essentially, I'm going to just keep going, and when I put in a 50, the last guy, I still get 8. And that might look daunting for just a moment, and then you realize, oh, I guess that would add up to be 400. How did I get that? I got 58s. 50 times 8 is 400. So this particular sum, this partial sum, is called 400. Now, by the way, it's not that I got part of that sum. I got all of that sum. It's partial sums because these sequences often continue on infinitely long, or as long as I want, and I'm just adding up a part of that sequence. Okay? Now, write each of the following in summation notation. That's this Greek sigma, okay? So what I want to do is find some way to write it here using a k so that that's the list. And actually, I guess I should have had plus signs in here, but I want to add up the terms of this particular sequence. Well, let's see here. I want to start at 1. And how many terms do you see there? If I start at 1. Now, I know you say, well, I see 5. Think about the ones that I didn't write. Isn't that 99 of them? And if you first let k be 1, and then you let k be 2, and then you let k be 3, what would I do in order to get these? Well, do you realize it's just k itself? I know. These may seem really scary, but be brave, get started with them, okay? And especially if you start with working with ones that are given to you in sigma notation and writing them out, then this is essentially just going backwards. So it will be more comfortable to go in this direction. After practicing some of those, then going backwards won't be quite so scary. Okay? Well, now in this case, all of them were written. Again, I really needed plus signs. So I've got 1, 2, 3, 4, 5, 6 terms. So I'm going to start with 1, and I'm going to end with 6. Now this is the first term, k is 1. For this guy, k is 2. For this one, k is 3. Do you kind of see a pattern going there? Well, you know it's only the top numbers that are changing. So 2 going to a 4, 3 going to a 9, 4 going... Oh, these are the squares, aren't they? That's 1 squared, 2 squared, 3 squared. And notice that the denominator never changes, so it stays as a 10. Now, by the way, you might want to actually take this notation. If you're not comfortable, you might want to take this notation and write it out and see if, in fact, that is what we get. Okay? And the third one here, oh, this guy looks familiar, doesn't he? And again, get the plus signs all the way through there. Do you remember this guy from before? This is a 1/12, 2/12, 3/12, 4/12, 5/12, 6/12. So we know that it is something over 12. Isn't it k each time? Because this is first term, second term, third term, fourth term. And k is going from 1 up to 12. All right, look for patterns. And again, if you're having trouble with it, also really try to pair up. This is my first term, this is my second term, this is my third term. And of course, this is 2/12, 3/12, 4/12. 5/12. And as you try to pair up which term you're on, what k is equal to, it can help you in trying to figure out how to write those. Okay? Now this is, I'm going to take just a real quick second on this. I put this in here just to show you one of the reasons why we want to study sequences. Because there are some interesting number patterns, but there's also some great applications. So, what I'd like to do is, let's compute what x minus 1 is if we let x be equal to 1.2. Now, I know you may think I'm just totally crazy to want to do this, but go along with me. Well, I didn't need the help, but it's 0.2. Now, I want to add a second term. I have x minus 1 to the first minus x minus 1 squared over 2. Now again, I want to let this x value be 1.2. And you could grab a calculator and do all this computation, and what you get is 0.18. Well, then I want to add on to that, which we just computed, another term. That x minus 1, but this time to the third power over 3. And if you do that computation with letting x be 1.2, we get that decimal. By the way, you can kind of see we're getting closer and closer, maybe some value. And I continue this pattern for the fourth term and the fifth term, and I've computed those values. Again, you kind of see they're getting closer and closer to something. Now, by the way, alternating minus and plus might bother you a little bit right now, but do you realize that I essentially have x minus 1 to the k over k? Because here it is, 1 over 1, 2 over 2, 3 over 3. So you see that pattern coming out. Now you might say, so? Okay. Well, also grab a hold of your calculator and find the approximation for the natural log. We've done those already. Natural log of 1.2. Well, what your calculator tells you is 0.1823 to 5 places. And looky there. See, your calculator doesn't have a table of values in there that it just runs in and searches for values. It's doing computations, and it's using sequences in series, in all likelihood, from my basic knowledge, in order to come up with those values. And it's pretty sweet that we can do that. Okay? Now, by the way, this was a very specially constructed one. If you want some more help on finding log values, email me. Okay, quick recap. A sequence is simply a function. And as a function, it has inputs and outputs. Remember that silly video about the pop machine? You input coins and you output a drink? All right, in this case, we input positive integers and we output a list of numbers. Okay? Now, we can define that guy explicitly, which means you can go immediately to a particular term, or we can define him recursively, in which you must walk out term by term. When the terms of the sequences are added up, we call that a series. And I didn't want to try to get a sigma in here, so I just wrote the word sigma. The shorthand notation for getting a sum is that Greek sigma. Really, the notation might be what drives you the most crazy with this particular lesson. So really focus on what does this mean, okay? Work really hard on it, and I'll see you in the next lesson.